So recall that before the session, lunch session, we were talking about water distribution networks. We had a source, several sinks to which we want to provide water, and life was easier when you don't have loops. That means life is easy when you already know the flow in every link. Okay. Now we look at the case when you have loops. All right. So first of all, you can see that there is no unique value of Q that must flow through every link. Okay. So for example, if node 5 has a demand for 100 units, that 100 units can flow through 1, 2, 2 to 4, 4 to 5, and it can also flow from 1 to 2, 2 to 3, 3 to 5. Okay. So it is possible that pipe 3 to 5 has 100 units of flow. It is also possible that it doesn't have any flow. Okay. So even if I remove 3, 3, 5 link, I will still be able to at least connect all the nodes. Okay. It is also possible that 50 units come from 3 to 5, another 50 comes from 4 to 5. Okay, so that is one difficulty, that Q is no longer fixed, so now it is a variable. All right. The other difficulty is that I don't know the direction of the flow in any link. Okay. So for example, I don't know whether water is going to flow from 4 to 5 or 5 to 4. Okay. It is possible that due to different pipe configuration, the head at 5 turns out to be higher than the head at 4. So in that case, water will flow from 5 to 4. And if the head at 4 is higher than 5, then it will flow from 4 to 5. Okay. So that variable Q that we had could technically be negative also. That means it is flowing in the reverse direction. All right. So that means we have, two more broad difficulties. So suppose I knew that Hi is more than Hj, then I know that this is the relation. Okay. So water is flowing from I to j, and the head loss is going to be this. In this equation, I don't know dA, so I don't know the diameter that I need to decide, and I don't know QA. Okay, depending on the diameter, Q will change. Okay, so this is nonlinear as of now. Okay. Also, if I look at that direction of flow, okay, the constraint really is this. Okay, so I need to look at the sign of QA and then decide which way it is flowing. So a convenient way of writing the signed form is this. Okay, so if QA is negative, then Hi minus Hj is going to be negative. Okay, so that means water is flowing from J to I. Okay, if QA is positive, that means Hi is going to be higher. All right, and these two expressions are same when Q is positive. Okay, but and there is a sign difference when Q is negative. All right. So usually engineers like to write it like this. Okay. And now it has three terms. Okay. There is a mod of QA raised to the power 0.852, and the reason why we have written 0.852 as a power of absolute value of QA, because raising a negative number to 0.8 doesn't make, it gives you some imaginary number or a complex number. So we would like to keep things real. So that is why the sign is moved here, and we still are able to compute the power. Okay. So everybody with me? All right. So, so then how do we deal with this situation? So rest of my talk is going to be on the board, trying to simplify this thing, or to tackle it in some other different way. Okay. So so one way is to call a global solver like Baron or Cohen or Skip to 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 find the optimal solution. So rest of the constraints are similar, and if we assume that multiple pipes are allowed per link, then it becomes slightly more difficult. Let me show you. So, so if we say that one link is composed of smaller parts of varying diameters, then this Hi minus Hj would be equal to summation over k, similar to the expression we wrote in the earlier class, L k a times qa raised to the power 0.8 times qa divided by Ra 1.8 d k, okay, 4.87. Okay, so now if we write it like this, the bottom or the denominator is a constant. Okay, but I have a product of three terms. Okay, so I have, this is a variable. I don't know the length of each type of pipe, and I don't know the flow. Okay, so I get a trilinear term, one of which has a power of 0.8. Okay, all right, and this is quite non-convex. All right. If you just look at the curve of this part, so suppose I want to just look at how this power looks like. So you get a inverted parabola and a upward parabola. This is the curve for this function qa raised to the power 0.852 qa. Okay, so this is already non-convex. If I multiply it to another variable that is also a non-convex function, so it stays non-convex. Okay, and we would like to be exactly on this curve. Okay, so it's not that the feasible region is below this curve or above this curve. It is an equality constraint, so we want to be on such a curve. Okay, and if I take any 2 points on this curve and try to join that line, that is not on the curve, so it is obviously non-convex. Okay, all right. So so one way of solving is the regular branch and cut with spatial branching. And this is implemented in several solvers. So what they do is they try to create outer approximations of this curve and then refine it recursively by branching. Okay, so those techniques will be covered next week. But it is a similar process as branch and bound, but the branching is far more vigorous because here you don't have any integer variable, so you have to branch on very small intervals, and you really have to brute force your way to understand whether there are better solutions around or not. Okay, So this is implemented in several solvers like Skip and Baron, Kuhn as well. And one can give it to these solvers and let them solve. Our team tried it, and beyond such networks which have 7 or 8 nodes, they don't give solutions in reasonable time. Okay, so even after 1 hour, they keep trying to solve because they are looking for the global optimality. So there are other creative ways of attempting to solve this. There has been some effort to use MINLO solvers which are designed for convex MINLPs. So this is a non-convex MINLP. And convex MINLPs are much easier to solve. So some researchers have tried to solve it as convex MINLPs, but making some relaxation so that some global solutions are not missed. But those turn out to be similar to heuristics. Okay, there is no guarantee then you have reached the optimal. Another approach that that has come out recently, I'll post the reference material in the slides later, is this very simple idea that these loops create the difficulty. If there were no loops, then you would be able to solve it fast. Okay, so what you can try to do is break some cycles. So you force the flow in some of the loops or arcs to 0. So for example, how many arcs do I have to remove in this diagram so that there are no more cycles? 2, all right, and those 2 can be selected in many different ways. Okay, so so once you remove 2 arcs reasonably smartly, you are left with a spanning tree again, and you can quickly find a solution. Okay, and one possible way is to search over all those spanning tree candidates. Okay, the difficulty in that approach is that once your network becomes bigger, so suppose you have 20 edges and there are 5 or 6 cycles, then the number of combinations in which you can remove edges is too high. Okay, so suppose there are 20 edges out of which you have to remove 5, so then 20 choose 5 combinations you have to try. Okay, even after you remove those edges and get some feasible solution, it is not guaranteed that it is going to be optimal, because it is possible that in the optimal solution there is flow coming from both sides. Okay, so even if you set something to 0, set something to 0, the problem becomes easier, but then you might have missed some optimal point. All right. So then the next step is to not set it to 0, but estimate, get a good estimate of what a flow in this link could be and fix that number. So once you fix that number, then all the other queues might become determined, and then you might get an easier LP to solve. Okay, so that is one approach to attack this problem. Okay, the other interesting approach that has been tried is to have parallel imaginary edges in the same network. Okay, so you So what you say is that, so here we already know that flow is always going to happen because this is the source. Okay, in all other edges, I can add directional flows. So instead of having one arc, I will imaginary, add additional arc, and then assume that flow is positive in each of the links. Okay, so essentially we decompose QA as QA plus minus QA minus. Okay, and both QA plus and QA minus are positive entities. All right. And then if I write the expression, then this absolute value term goes away. Okay, so either flow will go this way or either flow will go this way. Okay, so at least there is some simplification that I don't have to deal with this absolute value raised to the power 0.852. I am back into the domain of LKA into QA times 1.852, okay, raised to the power. So that reduces the number of non-convex functions that are there in my function, and then try to solve it using again one of these solvers. Okay. Huh. What? Huh. So there are two cases. Either either this is positive or it is 0, and simultaneously this will be positive or 0. Yeah, so we have two variables, and the pressure loss will be written in both variables. Okay. So it adds some complexity because to be sure, you might even need an indicator variable saying that whether this is taking positive value or this is taking. So you might need one more binary variable if you want to be very precise about that optimization. Okay. So even if you get rid of this absolute value sign somehow, and if you already knew the directions, okay, or you are able to model them as two different flows in both directions. So either you have 1.852 if it is positive, or you have minus of QA raised to the power if it is negative. Still there is some non-convexity here because you are multiplying two variables, and this itself is a non-convex function like earlier. Okay. So this should be slightly better possibly than this, but what happens is that when you give it to solvers like these, for heuristics, inside these solvers are well-defined heuristics which try to find or guess some good solution before trying to prove that it is really optimal. So those heuristics suffer quite a bit because suppose I say that I am just going to solve this nonlinear optimization problem to local optimality. Okay, so forget global optimality. Suppose I want to solve a problem like this to local optimality. Even there, some of the solvers face problems, which is a very sort of an implementation specific problem, in the sense that suppose you add this constraint QA greater than equal to 0. So in a computer you store these values as floating point double values. And sometimes what happens that even if you say QA is greater than equal to 0, the solver may try to search at points very close to 0, and sometimes the candidate that the solver has found, it might have a value of -1 into 10 to the power -7 or something. Okay. And for all practical purposes, we may assume that this is 0, and it is 0 in fact, for all purposes, except that to verify optimality at this point, the solver will also need derivatives, okay, because gradient of f has to be close to 0, and since this is negative, this quantity, you can't even evaluate the function for a negative entry, so you have to be a little bit careful. And make sure that such values don't appear when you are doing these types of problems. Okay, so the solvers have to be told that if the candidate solution is slightly out of bounds, okay, then just push it a little bit more so that it doesn't cause numerical errors. Okay. All right, so that is one numerical difficulty that that is faced. The other numerical difficulty is, even if QA is strictly greater than 0 or equal to 0, the second derivative of this function does not exist when QA is 0. Okay, what would be the second derivative? Suppose I just have QA raised to the power 1.852. If I take the first derivative, it would be 1.8 QA times 0.852, and if I take the second derivative, what would happen? It will become QA raised to the power minus something, okay, and near 0 this is ill defined. Okay, so your Hessian, which you need sometimes to find good directions or to check for convergence, it might not exist. Okay, so again, even finding local optima for this problem tends to become difficult. All right. So what is the solution? Okay, so that I think is still quite open. Okay, there are a lot of people trying different things. Some things work for practically small cases. Most of these things don't scale up when you have larger networks. Okay, and typically these loop networks are found in more developed regions. For example, urban networks of water distribution, they have multiple sources and they have several loops. Okay, so the natural question is, why do you have loops in the first place? Why can't engineers just remove some links and make life easy for us? And the reason is, these extra links provide good redundancy and resilience. So if there is maintenance happening on this link, you will still get water. Okay, so or there is a breakdown or some other blockage, you will still get water. And sometimes there are multiple sources, so you might want to have things coming from two sources rather than one. Okay, for safety. Okay, so these are somewhat important. Okay.
With this definition of QA, it can be negative also.
Yeah.
This definition of QA plus minus, QA minus. Then QA can be negative also.
QA can be negative. QA is both positive and negative in the original model, but QA plus and QA negative, they will take only positive values. Okay. Yeah, so here I didn't write properly, sorry. Okay.
Sir, I think
Huh.
the assumption of demand being fixed is also quite not realistic. So bounding, so loop can overcome that also. Because if there is excess supply,
Yes. So there are a lot of practical reasons why you should have these loops. Okay. So so with some PhD students, what we are trying is a combination of some of these ideas. We are trying to guess some minimum cost spanning networks by formulating some different models and trying to guess some of the flows, then fix those flows, then solve some NLPs and get some solutions out. Because this Jaltantra team, they have tried a lot of solvers. In fact, they purchased commercial versions of Nitro, which is a branch and bound nonlinear solver, commercial, Baron, and they even tried this. Huh? Which one? Alpha ECP. Sure. And tried many different configurations with different number of threads, different starting points, different parameter values, and it turns out that none of these techniques overwhelmingly dominate other techniques. So there is no guarantee that if we use one setting, then we will always be doing better than what is possible otherwise. So so that way there is a lot of scope for improving things and adding additional features which the engineers would like to have. So so that is it for now. Hopefully, when we meet next time, we might be able to give you some updates of what has happened in this particular question. Okay. So with that, I will stop.